people who did stuff.
I did everything first, and then it came back to the first one, and then did that.
There were people who did stuff, but I don't think anybody did that would prove right. But I'll show you that one later. Logan asked this in class on what's that, Thursday, about like what my if I have a replacement policy for tests and stuff, and I don't have a policy, but if you show improvement on the final, then like I will take that into consideration, right, when I'm doing final grades. So I'm being recorded now, so I have to be really careful about what I say. One time I said something and a student got a timestamp on it and sent it to me later to tell me it was a thing. So I have to be really careful about how I say what I'm going to say. But yeah. It was an example. It is fine. It was an example from the packet. I don't like the way that I said it. Anyway. There's good things and bad things about recording myself, right? Anyway, I should turn the screen on so y'all can see. Okay, so today we have the part 4, the notes that we're starting this test material stuff. We're going to do proofs for the first like couple of pages. Let's see, when do we stop doing proofs and start doing other random things? This bit is mostly for you computer science people. After about, I don't know, page 15, so halfway through this packet, we stop doing proofs. So you got just a couple more class periods of proof writing. Y'all got it? You got it in you? Maybe.
My arthritis might not happen.
Yeah.
So I have a question.
Yes. Yes, ma'am.
So I have been like anxiously checking Blackboard all weekend to see if the test grade and everything.
I haven't.
Just to like gauge, is there a problem here? Do I need to do something about this? Like, is there a way to?
I will have them graded tonight or tomorrow morning. I'll post them tomorrow morning. I don't think you need to be worried. Maybe they're all fine. I just feel really bad about the way that it feels, but it may be that they're fine. Right? What? Yeah, the bonus half of you left blank, so yeah. I thought I was done with those half of the tests, but then I realized that I didn't grade one of the problems at all. So that function wasn't on too, by the way.
No. Are you kidding? No way.
It's not on too. Those integers, and a lot of you were like, let x equal y plus 5/4. Notice x is in z. Oh no, it isn't always. That's the problem. That's not always an integer. I think somebody got this right, and somebody said, look, 0, 1, 2, none of them have pre-images in Z. Guy, it might have been you, no? Somebody wrote like they did a bunch of things. They were like, this is this, and like, you're like, somebody said 0, 1, 2 don't have pre-image. So wasn't any of you? Well, it was one of you. It wasn't on two, but those of you who wrote on to proofs, your proofs were good. Or if it was on two. Okay, so today we are going to talk about relations on sets, and then we're going to move into talking about equivalence relations. This is my favorite thing to teach. These are my favorite kinds of proofs to write because you get to, it's the same thing every time, and they're involved. And so when you finish, you feel like you've accomplished something, but none of the parts are very hard. Does that make sense? to somebody else looking on or to you when you're done, you've written a full page proof, you're like, yeah. They're like, none of the parts by themselves are that difficult. That's why I like them. And it's the same thing every time. Okay, so we have relation on A is a subset of A cross A. So this is confusing. The terminology here looks confusing. So we have this relation R that's a relation between two sets from A to B. Hold on, let me draw a picture. Pictures help. So like if A, this is set 1, 2, and B is the set A, B, say. We would define a relation A cross B, the Cartesian product is a relation. So we would define that as like 1A, 1B, 2A, 2B. So the ordered pair 1A is in the relation R. Not equal to R, is an element of R. So you get this like, think about like a function, right? The ordered pair that satisfies a function that's in the relation, that relation is the function. Does that make sense, y'all? You have an input and an output, right? Yep. And the ordered pair satisfies the function. So, but this doesn't have to be a function, just a relation. It's just a set of ordered pairs, right? That's what a relation is. If we were in college algebra, we would define a relation as a set of ordered pairs. A function is a set of ordered pairs where every input has exactly one output, right? Yeah. So a relation is still just like a set of ordered pairs. So X is related to Y, and we're going to write it like this, X, R, Y, if and only if the pair X, Y is in the relation R. So remember our Cartesian product, which was on your exam, elements in A cross B, what do they look like? They look like ordered pairs, yeah, maybe. Where A is in A and B is in B. Right? Right? Okay. So some examples of relations, I just said this, a function. Every function is a relation, but not every relation is a function, right? So for any function f from A to B, the relation is going to be the set of all ordered pairs A, f of A. We're thinking about x, f of x, right? So this is the set of the things in the relation. You're talking about A being related to f of A in that notation. For your bubbles here, you have A and f of A. This is in A, this is in B. And your function f is between them. It is related to by the relation R. This works for multivariable functions too. So if you're thinking about a function f from, let's say, R cross R to R, so your like ordered triples here would be x, y, z. Yeah, y'all with me? Yes? No? So the things in this relation are going to be ordered pairs x, y in the first spot, and then z goes in the second. This is where your ordered pair x, y is in R cross R, and z is in R. So what that means is that x, y is related under this function to the element z. So any graph in R2, so any graph in the real plane, that's R cross R. X is related to Y. Or your relation R is all ordered pairs X, Y, where X, Y is on the graph. for this circle, right, X would be related to Y. Let's say that this is the unit circle, right? This would happen if and only if X squared plus Y squared equals 1. Right, the relation there is that X squared plus Y squared equals 1. Are you kind of understanding what's happening here? A relation is taking just a set of ordered pairs. It's an input that goes with its output, but it's not necessarily a function, right? It's just how two things are related to one another. So like for number 4, here's an example. A is US cities and B is US states. So we can define this relation by saying that like element A is related to B if and only if city A is in state B. So this relation R would consist of the ordered pairs A, B, where city A is in state B. Do you have questions about what a relation is? That's not a question. Do you have a question? Let's think about this relation, y equals x squared. This is a relation, it's a function, yeah? So what things would be in this relation? So x is related to y if and only if y equals x squared. So some things that would be in this relation are, would be 1, 4, 2, 4. Yeah, 3, 9. I didn't say that. Every function is a relation, but not every relation is a function. Yeah, so any example of a function works as an example of a relation. Well, a function, right? Every input has one output. So if an input had 2 different outputs, like 1/6 being in here would make that not a function because one maps to 1 and one maps to 6, and that's bad. It's not actually a function, right? 1-to-1 for function stuff is that you don't have 2 arrows going to the same spot. It not being a function means you have 2 arrows coming from the same spot and going to different places. That's not a function, right? But that still works as a relation, right? So if this was A, B, C, D, and this is 1, 2, 3, 4, right? A1, A2, B3, C3, D4, whatever. Those ordered pairs work as a relation, but they don't work as a function. Does that make sense? Well, from R to R. A function of X. Is that okay? Yes? No? Did that make it worse or better? You think better? So this relation, if we were to define this relation would be the set of all ordered pairs A1, A2, C3, D4. That's this relation. Yeah? Yeah, that's what this is trying to say in a lot of math speak, but yeah. So X is related to Y if and only if that ordered pair is in the relation. Which has some definition, right? And this one, it's this example down here, it's city A and state B, right? So the examples of things that would be in this relation are what? It would not be one to one then, right? Because your inputs can't repeat, but your outputs can. Does that make sense? So for a function, you can't have two arrows coming from one input value. But you could have like, I don't know, you could have Columbia and Charleston both mapping to right. I mean, we shouldn't talk about Springfield or something because there's one in every state. But like in theory, right. We would know which one we were talking about. Yes. But like right now, we're not really going to be looking at the difference between relations and functions at all. That's not really the point of what we're doing. But it's not.
Is this something we want?
College algebra. A relation is a set of ordered pairs. Yeah? A function is a special type of relation where every input has exactly one output. No? Me just, let's. This is a relation. Yeah? I have no idea what the actual relationship is between these input output values, these X and Y values. I don't know what it is. Just made this up, right? A function is a special type of relation. Where every input has exactly one output. Every time you push the cherry Coke button, you get cherry Coke. Right? When you plant an apple seed, you get an apple tree. If you get something different, then the thing's not functioning, right? When you press the gas in your car, if your car does not go faster, then your car is not functioning, right? It as a machine is not working. It's not doing what it's supposed to be doing. So how do I fix this relation up there and make it a function? Yeah, these guys are a problem, right? This one is related to 2 and 1 is also related to 3, and that's bad. That means I pushed cherry Coke or I pushed E5 and I got Skittles one time and one time I got M&Ms. And they might look the same, but they're not the same, right? And that's a problem. Something broke in the machinery of the vending machine, right? It's a machine because it functions the way it's supposed to. And when it doesn't, that means when you do something, it's not having the right reaction, right? If that reaction is a guessing game, that's not fun for anyone, right? So like what we're doing looks different than that, but it's not really different. You've been doing this for a long time. This is where domain and range come from. Input, output values on the left, output values on the right, domain on the left, range on the right, or codomain. Yeah. Right? That's why you didn't specify in college algebra or whatever between the range and the codomain, because you were looking at something like this where you're looking at the range. You don't need to talk about what the codomain is, right? So this isn't actually a new concept. It just looks hard because it's in discrete and in math text, and it looks harder, right? This is a thing that you know. Okay, so it's a set of ordered pairs. The ordered pairs go together by some relation. That's really just the idea. We're gonna get to a point where we talk about these examples, and I hope it'll make more sense. Okay. So, we're gonna talk about 3 properties that could exist on for a relation.
Of what? Are you looking in the Zoom link? Because that's where they are. Well, they're all on YouTube. Except though Thursday was a test day, so they're all on YouTube. It should be up to date. They're all on YouTube. Okay, so some properties that a relation can have. A relation can be reflexive, symmetric, or transitive, and we'll talk about what each one of those things means one at a time. So a relation on a set R is reflexive if every element is related to itself. Think about looking at your reflection in a mirror. What are you looking at? If I was looking at Ruth, when I looked into the mirror, that wouldn't be a mirror that was working, right? Yeah. So a relation that is reflexive means that every element is related to itself. So that I does not go right there. There. So for every x in A, x is related to itself. For all x in A, xx is in R. That's written right here. I don't need to write that again. Okay, so we have some examples of relations here on this page 1 through 4 here. We're going to talk about if these actually are reflexive. Okay, so on this first one, example number 1, we have A is the set of all people in the world. R is the relation that consists of pairs of people. Remember, everything in a relation is an ordered pair in a set. So R is the relation that consists of all pairs of people X, Y, where X and Y have the same mother and father. Okay, so A is just people. The relation R is going to be the set of all X, Y, where X and Y have the same parents. So we are trying to decide, are these relations reflexive? So for every X in A, is X related to X? Or is XX in the relation R? The question you want to ask yourself is, does Whitney have the same parents as Whitney?
I think so.
Answer is yeah. For any Whitney, right? For any person that you choose, that person has the same parents as themselves, right? Yeah. So this answer is yes. This is reflexive because for every person, that person has the same parents as themselves. So like Whitney is in the relation R. Yeah, does that make sense? And Whitney is arbitrary. I mean, she's here, but like that was an arbitrarily chosen thing. Yeah, that works for any X that you choose. Okay, so the next one, number 2, this is more like mathy maybe. You have this set A that's just the numbers 2, 3, and 4, and the relation is that set of ordered pairs 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. And the question is, for this to be reflexive, is for all X in A, is XX in the relation. So no, this is not reflexive because 4 is not sitting in this relation. So under this relation, 2 is related to itself, so we're good to go. 3 is related to itself, so we're good to go there. However, 4 is not in this relation R. So that means because of this, that this is not reflexive. Right? To prove that for all things this thing doesn't work, you have to show that it doesn't work for one thing only, right? To disprove it for all statement, you need an example. This is your counterexample, is that 4 is not in the set, it's not in the relation R. So every element isn't looking at itself under this relation because 4 doesn't look at itself. Is that okay? Yes or no? Certain, not all of them are, no. Some of them are. Right. Because it has to be true for all. It doesn't matter that it works for all of them except for this one, because it doesn't work for that one. That's enough to disprove it, you know, to show that it's not true for all. Logan, what's up? Every number in here, its corresponding mate, yeah. And its mate needs to be itself. Yeah, yeah. Yeah, yeah. Since every element in A cross A isn't sitting in R, right? Yeah, it's not. This one, that's an element with a slash through it to see it's not an element of R. Okay, do we think we're okay? All right, number 3 here, we have A is the integers now. And the relation R is that you have these ordered pairs X, Y are in the relation if and only if X times Y is greater than 1 or equal to 1. Z2 is Z cross Z, yeah. So that's where those ordered pairs are coming from. Okay, so let's separate this stuff. X is related to Y if and only if X times Y is greater than or equal to 1. So for all, we're looking for reflexivity. So for all X in Z, is X times X greater than or equal to 1? Logan says no. Why say no? Because of 0. 0 times 0 is 0, which is, you know, not greater than or equal to 1. So this is not reflexive because it doesn't work for all of the X that are all integers X. This does not work. If we talked about just the natural numbers or non-negative integers, it would be fine, right? Because the number squared is positive, yeah. If you're talking about just the natural number. Okay, are we good or not good? We're okay? Mod stuff. You know mod, yes? What? Mod pizza is pretty good. It's really hard to get in and out of that place, though. Just don't go. was so bad. Okay, so also there's this place Blaze that does kind of the same thing and it's so much better. And so Blaze is so much better. Agreed. We don't have Blaze here though, right? Okay. No. Where are you from? Okay. So we have the integers here. That's what we're looking at. The relation is ordered pairs of integers. They're in the relation if and only if x, those 3 bars, that is congruence. But you can really look at this as x mod 7 is equal to y mod 7. So 2 things, an ordered pair being in this relation means that they have the same remainder mod 7, right? That's what y'all know, modular arithmetic stuff. Yeah. So like 14 is actually 0 under mod 7. Yeah. Okay, 15 is 1. Yeah. 16 would be 2. Yes, okay. So the question is, for this thing to work, is that for all integers x, is x mod 7 equal to y mod, to x mod 7, I meant. Yes, this is not a trick question. The answer is yeah, it is. This is an equivalence relation, folks. This is what we're working up toward. This one will work, yeah. This is a yes. Okay, so for reflexivity, you need to know that for every element in the set you're starting with, it has a mate under the relation that is its same thing. Yeah? So for every x, x is in the relation. X is related to itself under whatever the relations are. Which could be a function. Yeah? Questions or no? Because we're going to move on to symmetry. We're good. So a relation is symmetric if when x is related to y, then y is related to x. Or if xy is in this relation R, then yx is also in the relation R. Good? Yes? So when you start looking at when you're trying to verify something is reflexive, right? You start with an x in A, an arbitrary x in A, and show that xx is in the relation R, right? When we're doing symmetry stuff, what are we going to start with? Yeah, we're going to start with an ordered pair xy in the relation. And we want to be able to show that that in the reverse order is also in the relation. Yeah. So we have number 1 here, again, is the set of all people. A is the set of all people. R is the relation that matches people up who have the same parents, right? So R is the relation consisting of all pairs of people x, y, where x and y have the same mother and father. So we get to assume that x is related to y, and we want to show that y is related to x for symmetry. So in honor of my brother, because today is his birthday. So we have me and my brother. We are in this relation R because we have the same parents. Is it true? This is an example. Y'all are with me. I'm proving a point with an example. Is it true that this is in the relation R? That Drew Emily is in the relation R? Yeah, right? So this is symmetric. We're not proving anything right now. Yeah. This is just an example, it does not make a proof, yeah? But if X has the same parents as Y, then Y has the same parents of X, so that would be your proof, right? Is this. Okay, on number 2, we have 2, 3, and 4. Again, for our set A, the relation is the set of ordered pairs 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, and 3, 4. So the question is, for all X, Y, when X, Y is in R, is Y, X also in R? Why not? Right, that's good. So 2, 4 is in this relation R, but 4, 2 is not in R. So this is not reflexive, not symmetric. Is there anything else that would break this? Yeah, right, that's the other one. 4, 3. All the other ordered pairs, you can find their reverse thing there, like 2, 2 reversed is itself, and so is 3, 3. 2, 3, you'd be looking for 3, 2, that's there. 2, 4, you would be looking for 4, 2, but that's nowhere. 3, 4, you would be looking for 4, 3, but that's not anywhere either. So because they're like reverse of those ordered pairs isn't in the relation, then this thing altogether is not symmetric. Is that okay? All right, on number 3, we have this, we have A as the integers again. The relation is the set of ordered pair integers where X times Y is greater than or equal to 1. So for all X, Y in R, is YX in R? What happens if XY is in R? What do we know? You're answering a different question than I'm asking, I think. Right? What do we know about XY if XY is in the relation? That the product is greater than or equal to 1, right? So the question is YX also greater than or equal to 1? And the answer is yeah, it is, which is what Logan's actually answering. No, you're good, you're good. But the assumption here is that this ordered pair is in the relation. So 0 wouldn't be around. Because the 0 is not in there, right? 0 couldn't be X or Y because then it wouldn't be, that product wouldn't be greater or equal. Okay, number 4, again, we have the integers is our set A. The relation is ordered pairs of integers where they're in there if X mod 7 is equal to Y mod 7. So my question for you is to assume that X mod 7 is equal to Y mod 7. That's that X is related to Y. Everyone's tracking that, right? Yes or no? And then you want to ask yourself, is Y mod 7 actually equal to X mod 7? So is Y related to X? So this is also symmetric. How are we doing with that? Fine? Do you have any questions? Nothing yet. If they're reflexive, symmetric, and transitive, then it's an equivalence relation. We're working up to that. Okay, so we also want to look for the transitive property. So a relation R on a set A is transitive if when x, y, and y, z are in, hold on, let me write this better. X, y, and y, z are in R, then x, z is in R. Right, cutting out the middleman. That's what happens with the transitive property. So if x is related to y and y is related to z, then you should be able to say if it is transitive that x is related to z. All right, questions about that definition? Right, it's the same property it has been. One of these is identity, one of them is associativity, right? The symmetric stuff, that's associativity, that the order doesn't matter. So that is also a familiar property. And then this is that there's an identity, that the identity thing works. So that X is related to itself. Okay. So we want to decide, we have the same four examples of relations again. A is the set of all people. R is the relation on those pairs of people where X and Y have the same mother and father. So the thing you get to assume here, we want to assume that X, Y is in R and Y, Z is in R. The question for transitivity is X, Z in R? Yeah. So if you wanted to think about an example, you have me and my brother and my sister. They're both in this relation R. Well, also, so is the order pair of me and my sister. Yeah. Are we good there? It's a little bit harder on this one, I find. Yeah. No. Yes. But that's not enough to say it, right? Because that was only one example. Yeah. Yeah. So 2, 2 and 2, 3 are in R. So you want to know is 2, 3 in R, and the answer is yes, right? Because you just used that one. 2, 2, 2, 4, this works great when it's the same thing. 2, 4 is in R. So you're good. So we want to, like, you're looking for X, Y, Y, Z. So you're looking for the things that start with a 2s. We already did that, so we're done. Are y'all good? Right. But there's also no, because of that, it doesn't matter. Because there's not a second part of the chain, so the third part doesn't matter, right? We need the first two parts of the chain to work and confirm that the third part's there, right? So for the next one, we would have 2, 3, and I need to find anything that starts with a 3 to pair up with this. So I have 3, 2, right? I also have 2, 3, and 3, 3, and 2, 3, and 3, 4. Yeah? Yes? So the question is cutting out the middleman, is 2, 2 in the relation? Yeah. Is 2, 3 in the relation? Yes. Is 2, 4 in the relation? Yes. Okay, so we're good to that point. Everybody okay? See what's happening here or no? We're getting the first two x, y, and y, z, and r, and then we're trying to prove is x, z, and r. Yeah? We're doing this by exhaustion, which is exhausting. But like Charlotte said, this, if we start with 2, 4, we don't have a partner for it because nothing starts with a 4. Yeah? So we get to just move on. And we're going to move to the 3, 2. What would pair up with that one? 2, 2, 3, 2, and 2, 3. What else? Anything? Oh, yeah, 2, 4. 3, 2, and 2, 4. So I feel like I'm just writing numbers down. Are y'all tracking what's happening or no? I'm kind of not. Okay, so cutting out the middleman for each of those, we have 3, 2, 3, 3, and 3, 4. Are all of those in our relation R? Yes, good, good, and good. Okay.
Didn't have a pair.
No. For transitivity to work, for the definition of transitivity, you have to have this pair. No. When you have this pair, you have to have this. But if you don't have this pair, it doesn't matter. The thing is transitive if, x maps to y, y maps to z. It's transitive if you can say then that x maps to z. But if x maps to y and y doesn't map to anywhere, then you don't have to worry about it. Right. Then you don't have to worry about it. Yeah. The implication is irrelevant. Yeah. Okay, so I don't think we're done. We did 3, 2. We don't have to do 3, 4 because again that ends with a 4 and nothing starts with a 4, so we're fine. And everything is going to work with 3, 3. I hope that is obvious, but 3, 3, 3, 4, 3, 3, 3, 2. It's just those things. It's 3, 4, and 3, 2, which work. Yeah. So this is transitive. Huh? You did know, but you only did it for one example, which is not good enough. Right. Right. You can't be. Okay. The next one we have again we're looking at the integers for our set that we're pulling from. Our ordered pairs are integer ordered pairs. And they're related to one another if their product is greater than or equal to 1. So we want to know, we want to assume x is related to y and y is related to z. That means that x times y is greater than or equal to 1 and y times z is greater than or equal to 1. Everybody good? Yes? We want to know is x times z greater than or equal to 1. The answer is yes. But why? If x times y is greater than or equal to 1, that means that x and y are either both positive or both negative. Right? Neither one is 0. Yeah? Because it wouldn't be any relation to the other one. Yeah? So if x times y is greater than or equal to 1, that means they're both positive or both negative. Yeah? And y times z also greater than or equal to 1, they're both positive or both negative. Yeah? But y is in both. Yeah. So the positivity of y or negativity of y forces x and z to have the same sign also. Yeah. which forces x times z to be greater than or equal to 1. Again, neither of them is 0, so their product has to be, well, can we break this? Oh, we're integers, so we're fine. So you can break this with fractions, but we're not using fractions, so it doesn't matter. You have two integers whose product is greater than or equal to 1. That means both of the integers themselves are in absolute value greater than or equal to 1, right? And they're either both positive or both negative for x and y and z, but that forces x and z to both be positive or both be negative. So this is transitive. All right. Next up, our mod stuff. So we are going to assume that x mod 7 is equal to y mod 7, and that y mod 7 is equal to z mod 7. Your question is, does it follow that x mod 7 is equal to z mod 7? Yeah. So this is also transitive. Yeah. Do you have any questions about this at all? No? Okay, so a relation on a set A is called an equivalence relation if it is all three of those things: reflexive, symmetric, and transitive. And we get to use fun notation when we know it's an equivalence relation. You get to use a squiggle. Two elements A and B that are related by an equivalence relation are called equivalent. And you can use the little notation with A is related to B or A is equivalent to B under this equivalence relation. So X, related to Y becomes X squiggle Y if it's an equivalence relation. And again, it's an equivalence relation if it is all three of those things: reflexive, symmetric. What we're going to do right now is decide those things. Again, we still have our same 4 examples, so we want to recall now if they are reflexive, symmetric, and transitive to decide if they are equivalence relations. So the relation that has people paired up with a thing if they have the same parents, right? We decided that was reflexive, right? Because I have the same parents as myself, or Whitney has the same parents as herself. It is symmetric because X related to Y means that Y is related to X. X and Y both have the same parents. It is transitive because X and Y having the same parents and Y and Z having the same parents means that X and Z have the same parents. So this is an equivalence relation. The next one we had was this set A, that's 2, 3, 4, and the relation is that set of ordered pairs 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. We just went through an exhaustive thing to show that it was transitive. But because 4 is not looking at itself, it's not reflexive. And because 4, 2 is not in here, it's not symmetric. So this one is not an equivalence relation. All right, now we have number 3. we were looking at these ordered pairs X, Y, where they're in this relation if X, Y if the product is greater than or equal to 1. We decided that this wasn't reflexive because 0 is not related to itself, right? 0 is an integer, however, 0 times 0 is not greater than or equal to 1. We did decide that it was symmetric, and we did decide that it was transitive, though. Symmetric because x times y is greater than 1 means that y times x is, and then transitive because of the like sharing the signs. So this is still not an equivalence relation because of that reflexivity. Okay, and then lastly, we had that mod stuff. Now I told you that this meant congruence or equivalence, so we would hope that this one is an equivalence relation, or we've just totally botched it, right? And it is. We proved that x mod 7 equals x mod 7, so it was reflexive. We proved if x mod 7 equals y mod 7, then y mod 7 equals x mod 7, so it's symmetric. Then we did transitivity. X mod 7 equals y mod 7, y mod 7 equals z mod 7, means that x mod 7 equals z mod 7. So this one is an equivalence relation. Okay. The hardest part of all of this, I think, is probably talking about equivalence classes. So we have an equivalence relation R on a set A. The set of all elements that are related to a specific element is called the equivalence class of A and is denoted as that thing. Square brackets around the A. That's the equivalence class of A. So I want to go back up here and do this with these. What is the equivalence class of 2? Under this relation, the equivalence class, remember, is the set of all elements, that are related to 2. 2, 3, and 4. Yeah? What is the equivalence class of 3? Oh shoot, I shouldn't do this on a thing that's not an equivalence relation. That's really confusing. Whoa. Let's do it here. What is the equivalence class of myself? So me, my brother, and my sister, right? Does that make sense? Yes. What is the equivalence class of my brother? Yeah. What about my sister? Is my brother or my sister going to be in any other equivalence class? My brother or my sister, would they show up in Whitney's equivalence class or anybody else's equivalence class? No. If we had to divide up all the equivalence classes in the whole wide world, all of the equivalence classes in the whole wide world, everybody would appear one time, right? Yeah. And there's going to be either two equivalence classes completely overlap, like I do with my brother or my sister, or they don't overlap at all. Is that making sense? If every element is related to itself, then every element is in its own equivalence class, right? That's the reflexivity part of an equivalence relation. Symmetry is going to hit these things going both ways. That my brother and I have the same equivalence class. So the equivalence classes, if you were to union them all up, we're looking at unions of sets here. So if I unioned up all the equivalence classes under a relation, then I would have my whole set, right? I would get all of the set A. But none of them overlap unless they completely are overlap. Do you get what I'm saying? No. The equivalence, my equivalence class under that relation with the parents thing is not gonna overlap with anybody else's equivalence class unless it's my brothers and my sisters, and then they're the same. Yeah. Huh? Right, yeah. So the equivalence class of A is gonna be a set of all elements X in A where X is equivalent to A or X is related to A. So everything in A fits in one equivalence class. Only one. Those are called partitions of A. The easiest place to see partitions and equivalence classes is mod arithmetic stuff. I'm gonna scroll to that as soon as y'all are done writing it down. I'm gonna scroll there and talk to you about that. So a partition, these are disjoint subsets. Oh. Whose union is the whole set. So I'm gonna go find it for you. Mod arithmetic is the easiest place to do this. So if we think about remainders of a remainders mod 5, right? You have the things that have a remainder of 0 mod 5 are 0, 5, 10, 15, 20. Y'all are with me, 25, 30, whatever. These would be the things in this set. Y'all are tracking what I'm saying? Also -5 and -10 and -15 and -20 and so on, right? Yeah. What's in the things that have remainders of 1? Well, 1, 6, 11, 16, 21, 26, 31. You with me? What has a remainder of 2? Well, 2, 7, 12, 17. Wow. 27, 32. Wow. Make an entrance, Alessandro. Right. All of those things have a remainder of 2 mod 5. Yeah. You see what's happening here? Once we have all of these, all 5 of these, we have all of the integers. Yes. Do any of these things overlap? No. This is the equivalence class of 0. This is the equivalence class of 1. This is the equivalence class of 2. This would be the equivalence class of 3, and that's the equivalence class of 4. Right? So each one of those things, they either overlap everywhere or they overlap nowhere, right? So the equivalence class of 0 and the equivalence class of 5 are the same thing. Yeah. So that's what the equivalence classes do. They partition your set into things that are equivalent. So if you look at people in the world, right? The like partitions or the equivalence classes of people who have the same parents, right? You have these little groups of people who don't, they're disjoint, right? Like there's no overlap unless they're all overlap. Yeah? No? I don't know what's happening. Yes or no? Hi, Bryson. What? It said that they have the same parents. We're talking biological parents, right? You have 2 biological parents, period. That's science, right? That doesn't mean that they're your actual parent, but like the DNA contributions, male and female. Yeah, that's what I mean. Yes. Okay, so those things those make up the partition. Those partition your set A into different things, where either they overlap completely or they don't overlap at all. So they're not different. Yes, so they're not different equivalence classes because those sets are the same. I love this question, right? These sets are the same. They're the same. So the equivalence classes are not different. you can represent it like this or like this, but the equivalence classes, because they're these sets, are not different because the elements in the set are the same.
There's not like one that.
Yeah, or diamond, right? Yeah.
Yeah.
You could call that equivalence class any of those three things, yeah. But the set isn't changing, so your the equivalence class is the same. The representative can be different. Does that make sense? Yes or no? Let's, before we go, because we have 3 minutes, how about we come up with, let's not do, we're not gonna prove it's an equivalence relation because we don't have time, but let's do some equivalence classes under this. So we have our set A is z toss 0, so all integers except for 0. We're saying that A is related to B if and only if A times B is greater than or equal to 0. So pick a number, any number. Alrighty. So let's talk about the equivalence class of 7. Wow, that's not a very good way to write that. Let's talk about the equivalence class of 7. This is going to be the set of all elements x in z toss 0, right? Where 7 times x is greater than or equal to 0. What sorts of things would x be? But 0 is not in our thing, so we don't have to worry about it, right? So it's z plus. Anything positive that you multiply 7 by is going to keep that product positive. The fact that that has an equal to 0, yeah, we could, in theory, use 0 also, but that's tossed from our set A, so we don't even need to think about it or worry about it. Yeah? Give me another number. Is the equivalence class of 2 different than the equivalence class of 7? Why? Because it's in here. If they overlap at all, they overlap completely. Yeah? What would you multiply by 2 to get something that is not negative? Something positive, right? So this is equal to the equivalence class of 2. Give me a different number. Is that going to be the same or different? Give me something different then. Do a negative number. All right. What negative number you want to do, Logan? Okay, -3. This is going to be the set of all x in z toss 0, where -3 times x is greater than or equal to 0. What has to be true about x? It has to be negative. Give me another number. Let me ask you a question. Do we have all of the equivalence classes that are possible? Why? Yeah, why? Any other number we pick is going to have the same equivalence class as either this or this, right? These are, we're not talking about the real numbers, we're talking about this, right? Toss 0. So this is set of all positive integers. That's going to be, that's one equivalence class. The other equivalence class is the set of all negative integers. Yep. They union up and make this. That's how you know you're done. Yeah. Their union is the whole set A, but they're disjoint. They don't have any overlap. Yeah. Then that's how equivalence classes work. And on Thursday, we'll continue doing this. Have a great day. I'll see you Thursday. I'll get your tests in Blackboard tomorrow. Homework. I would do homework. I would do some homework. I don't know where we are, what we know. Hold on. What do we know? Does anyone know what we know? This is 8. 8-1, 8-2, and 8-3 we have, so 8-1 and 8-2 we're done with. What, do you have homework from 8.1 or 8.2, written homework? You don't know. You do. You guys, look. You could do all of homework 11. Let's say homework 11 is due on Friday. That means on Thursday you will have tried it and you will have questions for me, right? Okay. Wait, you won't be able to do the worksheet yet. Do the book problems. Do the book problem.